Hello, everyone, dear professors and researchers. I'm Zhang from China, Fuzhou University, and a young teacher. It's my great honor to give a report here. Today, my topic is AI-driven optimization of 3D printed short carbon fiber reinforced composite grade structures. Today's topic will include 4 parts. First of all, let's start with the introduction. As most of us know, composite structures has many outstanding advantages, including lightweight, high specific stiffness, and high specific strength. And nowadays, the rapid development of 3D printing bring the designers many advantages, including high designability, near net shape fabrication without mold, and promotes the diversity of grade structures. So my topic today will focus on these grade structures, which has many good mechanical performance, including bending, torsion, impact damage resistance, and it could be applied as supporting framework, core of sandwich panels, and protecting failures. And recently, the rapid development of AI technology maybe help us to design the 3D printing the grade. AI-based design and optimization will bring the more lightweight and high performance structures. The second part is materials and the method. We introduce FDM 3D printing as the fabricated method. And the 3D printing could create the parts layer by layer and the stacking. We use short carbon fiber as the reinforcement, which is commonly used in FDM. And the carbon fiber has 15 times high tensile strength than the matrix. So it could increase the mechanical performance significantly. First of all, we designed 5 basic configuration and 1 optimized configurations by changing the hole size along the x direction and both in x and z direction, following the linear or quadratic pattern. It should be noticed that in the SZ configuration, 3 geometry parameters were included, and in the SQZ configuration, 4 geometry parameters were included. So we separated the structures in 2 groups. In this page, we could see the dimension of the structure configuration and some pictures we captured in the experiment. 3-point bending testing were performed following a quadratic mode with the speed of 2 millimeters. And then we built a finite element model for analysis based on the 3D parametric geometry modeling using the commercial software CATIA. And then the FEM analysis were performed using the abacus, of which the dynamic expected element step were adopted. And we also use the general context, and in each model, there are more than 18,000 matches. It should be noticed that the global size of the grid structure is 1 millimeters, and the C3D8R elements were adopted. And then we use AI-assist optimization to get the final structures. In first step, machine learning surgeon models were adopt to predict the specific stiffness and the specific strengths. By using the touch-boost machine learning surgeon models and based on the Abacus simulation results, we predict the specific strengths and the specific strengths of 3D printed grid structures. It should be noticed that the database is very small. We only do 5 experiments and about 200 FEM analysis. And in the second step, the optimization of structure parameters was performed using the NSGR2 multi-objective optimization design method. And in the third part, first of all, we test 3 basic configurations, which could be used as the benchmark for FEM and machine learning. Then the experiment shows that the changes in diameter along x direction and the drop angle along the z direction can both reduce weight and increase the specific strength and the specific stiffness. While changing the geometry parameters have a very big impact in the peak load, it hardly changes the failure displacement. And in these 2 pictures, the high actual value indicates that the reliability of the machine learning model. And it means that we could use the machine learning model to replace the FEA. And in this picture, we see the optimization process. First of all, as the integration process, the orange curve gradually rise, means the goal parameters go high. And when we compare with the red dots and the blue dots, we could see that the quadratic configuration is much better. And then we do the FEM and the test to compare the optimized result. Both of them show that the optimization configuration has the least mass and the highest specific strength and stiffness. And in the experiment, the specific strength and the stiffness of the optimization configuration will increase by 14 and 28% respectively when compared to the original one. And the FEM also could give us more information, such as stress distribution and the damage evolution. We could divide the damage evolution into 3 stages. Firstly, in the inner stage, the minor damage could be seen and is very local. And secondly, the damage propaganda and the continuous fracture of the entire row in the element could be seen. And finally, in the structure failure stage, we could see many multi-row damage. And finally, in the last part, we do many multi-materials verification to see what our optimization configuration perform in other materials. And in the picture, we could see that it performed very well. And among these materials, the carbon fiber reinforced high temperature polyimide exhibit the best. Some conclusion could be drawn. First of all, the AI optimization framework effectively solve the bottleneck of traditional design methods and achieving a significant performance breakthrough. The grid structure is an ideal carrier for achieving lightweight and mechanical properties, and its performance is highly dependent on the geometry configuration and also the materials. The present method pursues high validity and broad energy engineering application as prospect. Thank you for your listening.